Okay, let me welcome you to this third lecture of our course. This lecture is going to have two parts. One is going to be on linear quadratic problems, a continuation of what we were doing at the end of the previous lecture, one-dimensional linear quadratic problems, the solution via Riccati equation. And then we're going to discuss approximation in value space in the context of these problems, and how Newton's method can be used to visualize the relationship between online training and online play. Then in the second half of the lecture, we're going to discuss issues of how you formulate problems, practical problems as dynamic programming problems, how you reformulate them to fit the canonical format, and we're going to give some examples of reformulation. So here is the outline. We first review infinite horizon linear quadratic problems, and we are going to focus on visual representations and visual interpretations. Then we're going to go into approximation in value space in the context of these linear quadratic problems. First with one-step look ahead, then with multi-step look ahead and truncated rollout, which is a little bit more complicated. And that's going to be the end of the first part of the lecture. We're going to take a break here. Then we're going to come back and discuss problem formulations by dynamic programming and give some examples. There is this technique of state augmentation that's going to be important. It's a very, very useful technique across the board. And we're going to illustrate this in terms of a couple of examples. We're also going to talk about some other reformulations. Particularly, we're going to see how multi-agent problems can be fruitfully reformulated. And then also partial state observation problems, what we call FOMDP, can be reformulated in terms of our dynamic programming form. So let's go into linear quadratic problems. Now you remember we were discussing one-dimensional deterministic linear quadratic problems where the system is linear. Xk is a state, it's a scalar. And Uk is a control, it's a scalar also. And A and B are known scalars. So this is a linear one-dimensional system. And the cost function involves quadratic cost, a quadratic cost on the current state and a quadratic cost on the current control. Q and R are positive numbers and express our desire to keep the state near zero and to keep the control also near zero. And the Bellman equation for this problem is what you see here. We minimize on the right-hand side the one-stage cost, this, plus the cost to go from the next state where we land. And when the right-hand side is equal to j sub x, we have that's the equation that corresponds to state x. Now x here is it takes an infinite number of values. It's a scalar. So there's an infinite number of these equations, a functional equation. But if we solve it somehow, then we're going to be able to get the optimal cost function. Now there's also another Bellman equation corresponding to a linear policy. Nu sub x equals L sub x, linear in the state. L is the linear cost coefficient. And now this equation has this form. And it's simpler than this because it does not involve minimization. It is like the Bellman equation for a fictitious problem where the only control available at state x would be just Lx. So plug in Lx in place of u, we get L squared x squared. That's where this term comes from. And plug in here Lx in place of u, that's where this term comes from. And now this equation is simpler because it does not involve minimization. And we're going to simplify it even further. So these are our Bellman equations, and we make a guess here. We try quadratic solutions, J's, which are a quadratic of the state, with K being the coefficient of the quadratic. So we try this kind of solution in here and this kind of solution in here. And then what happens if we, let's say, take this and plug it into here, this becomes quadratic in U, okay? And this minimization can be done explicitly in closed form by taking derivative and so on. And we can calculate the U that minimizes, plug it in, and then what we're going to get is a quadratic on the left side and a quadratic on the other side, which is given by this form through this minimization. And by canceling out x squared on both sides, we get this equation here. This is called the Riccati equation. And it is basically this Bellman equation restricted on the subspace of quadratics after we also cancel out x squared. If we do the same thing on the L Bellman equation for a given L, plug in this in here, then we're going to get a linear equation in K, which is this one here. Okay. The calculations are standard. You can do it. In fact, I think we also did it last time. So Bellman equations and the Riccati equations, which are restrictions to quadratic functions. And now, if we can find a solution to this equation, which is positive, K star solves the min Riccati equation, then we have a solution then we have the optimal cost function. That's part of the general theory, that the optimal cost function solves Bellman equation. Turns out it's a unique solution that's positive here. And we also, given K star, we can minimize in the right-hand side of Bellman's equation and obtain the optimal policy, mu stars of x. And you can see here that it is, on the right-hand side is quadratic. The minimization is over quadratics in U. It can be done again in closed form. And after you do all the calculations, you find that the optimal policy from this calculation is L stars of x. It's linear. And L star is a coefficient that's given in terms of K star by this formula. These are standard formulas in linear quadratic problems. And incidentally, the name linear quadratic refers to linear system and the quadratic cost function, but it also refers to quadratic cost functions, J star quadratic, and optimal policy linear. Okay, so it's linear quadratic in two ways. Great convenience, and that explains in part the popularity of the fundamental role of linear quadratic problems in control theory. Now, okay, so one possibility is to solve this Bellman equation, but there's also algorithmic possibilities. And we have discussed last time two basic algorithms for infinite horizon problems. One is value iteration. And what it does is basically iterates using this recursion here. And starting with a quadratic, the value iterates are quadratic also of this form. So K0 is the starting quadratic, KK is the kth iterate, and it's generated by this formula here, which is equivalent to this Bellman equation. So that's the value iteration algorithm, and we'll come back to it shortly. And there's also the policy iteration algorithm. And it turns out that starting from a linear policy, it generates linear policies. Through a cycle of a linear policy, it has quadratic cost function, which generates by minimization a new linear policy, and so on and so forth. Okay, we'll come back to policy iteration later. But for the moment, we want to interpret graphically the Bellman equations. And the equivalent form the Riccati equation, which is given by this, which is the Bellman equation on space of quadratic function. Okay, this right-hand side here is given by this red curve here. F of k is this expression of k. It is nonlinear, but concave. You can verify that it is concave analytically or graphically. And it has the form that I give you here. It has an asymptote at this horizontal asymptote at this level, a vertical asymptote at this level. And now let's go to the solution of this Riccati equation. To solve it, we have to find a point where the right-hand side is equal to the left-hand side. Now, the right-hand side is this red curve here. The left-hand side is linear. It's just a 45-degree line. And at the point where these two, the red and the black, meet, we have solutions of the Riccati equation. And we're looking for a positive solution, which is the optimal cost, the coefficient of the optimal cost function, which is k star. So this is a solution that we're looking for. There's another solution here that's negative that do not concern us because we know that the optimal cost is positive. So graphically, this is the solution of the Riccati equation, and we are going to interpret all algorithms and all operations, including reinforcement learning and approximation in value space on this figure here. But first, we want to give a graphical interpretation of the L-Bellman equation. Okay, so this is a little bit more complicated. We have the mean Riccati equation, which is this red, has the right-hand side, this red curve. And we have the L-Riccati equation, which corresponds to a linear policy. Nu equals mu sub x equals L sub x. And it is given, its right-hand side is given by this expression as a function of L, okay? And the L-Riccati equation wants to make the right-hand side equal to the left-hand side. So the coefficient, the solution of the L-Bellman equation and the coefficient of the corresponding cost of the linear policy is what you see here, right? The place where the green curve meets the black curve, meets the green line meets the black line. Now, notice that this figure is valid if A plus BL has absolute value that's less than 1. Why is that? Well, if in the case where, if this is true, then this green line has a slope that's less than 45 degrees and intersects the black line on the right side of K star. If, on the other hand, A plus BL is greater than 1, then the slope is greater than 45 degrees, and the intersection is somewhere else, which is not of interest. So what's going on here? If you look at the closed loop linear system, when we use as policy, as control policy, L times X. So the closed loop system looks like that. And if A plus BL is less than 1, then absolute value less than 1, then xk plus 1 goes down asymptotically towards 0. In other words, the corresponding closed loop system is stable. It goes either like that or like that, okay? Asymptotically to 0. And on the other hand, if A plus BL has absolute value greater than 1, then the state of the system explodes, either like this or like that. And the cost function is infinity for all x except for 0. And in this case, we say that the closed loop system is unstable. So there's an important distinction here between stable linear policies and unstable linear policies. And this is what you see here. On the other hand, the green line always lies above the red curve here because it's okay, you can verify this. This corresponds to minimization over those. And this picture is realistic. And for a slope less than 45 degrees, it gives us the cost coefficient of the corresponding to a linear policy. Are there any questions about this figure here? Okay, so now let's go further along this line. We have the min Riccati equation given by this red curve. And we also have this L Riccati equations, which are all of these lines, which always lie above the red curve. Now, it turns out that the red curve can be obtained as the lower envelope. In other words, if the area underneath the red curve is the area underneath all of these blue lines. And these lines come down to being tangent. They can be brought down to being tangent to this red curve. And that's what we mean that the min Riccati operator is the lower envelope of the L Riccati. Or the min Riccati graph is the lower envelope of the L Riccati graphs. And how do we see that? Okay, so if we plug in a quadratic cost function into the Bellman equation, this is what this is how we calculate f of k. It's minimization of u of this quadratic expression. Let's break down the minimization in two. First, minimize over linear policies, and then minimize over L. Now, if we minimize over u equals L sub x, then what we get is through the standard calculation for Riccati equations, we get this thing here. Okay, I have reversed the order, and this is just the expression for the L Riccati equation. So the upshot is that f of k, the red curve, is equal to the minimum of these blue lines. That's what this says, with f of L sub k being this. And moreover, there is these blue lines coming tangent to the red curve. And for a given k, for example, there is a tangent here. And it is tangent because this is a concave function. If it were not a concave function, then it would not be tangent. It would be, okay, it would intersect multiple points and so on. So now from here, we're going to go into the interpretation in terms of Newton's method. So let's look at approximation in value space. And let's remember our basic figure. I'm showing here approximation in value space with one-step look ahead and no rollout. Okay, this is the alpha. This is a simpler version of the alpha zero architecture. There is online play and there's offline training. The offline training is in the form of a cost function approximation that involves a quadratic cost coefficient. And the online play consists of, at a given state xk, we consider minimization over all controls, and then for including the one-stage cost, and then we add the optimal cost to go as quantified by the terminal cost function approximation. And now I want to claim that this is a Newton step for solving the Riccati equation, or equivalently the Bellman equation after x star has been canceled out. So that's where we're headed, and we're going to do a visual interpretation and proof of this. Okay, you're supposed to know about Newton's method because you've learned it in calculus. perhaps even some of you learned in high school, but I'm going to remind you. Remember, we want to solve this equation, the Riccati equation. So we're going to look at a generic equation of this form. G is a generic differentiable function. So here's the graph of G, and we want to find a solution of this problem. And the solution is obtained at the point where the right-hand side meets the left-hand side. It's this. There's another solution over here also. How does Newton's method work? It's an iterative method. Starts from some y0, generates y1, and so on. At the typical iteration k, we have the current iterative yk. And what Newton's method does is it linearizes G at the current point, linearizes by a first-order Taylor series expansion. And the linearization is this, using the gradient of G. And the linearization corresponds to this tangent line. And then Newton's method solves the linearized problem, which is this, okay? Instead of G, we use the linearization to obtain the solution, which is yk plus 1. So this is the graphical interpretation of Newton's method. At the current iterate, linearize and obtain the solution of the linearized problem. And at this point, we linearize again, find the solution of the linearized problem, and proceed. And this is a very, very fast iteration. It has quadratic convergence rate. Newton's method is the powerhouse of numerical analysis and numerical algorithms. Newton's method is sort of an ideal. All other methods sort of try to come close as possible to Newton's method. On the other hand, Newton's method involves some overhead here. In multiple dimensions, there's an inversion of this becomes a matrix, and there is an inversion, and so on. But Newton's method is the ultimate in efficiency and speed of convergence. Now, one of the difficulties here that you might wonder about is that this figure applies to differentiable functions. On the other hand, the Riccati equation is differentiable, but in general, in dynamic programming, we have non-differentiable Bellman equations. It turns out, however, that Newton's method admits a straightforward extension to non-differentiable right-hand sides, and in particular to the case where the right-hand side, instead of being G differentiable, is the minimum of differentiable functions. This is an easy proof, and you can find it in your textbook lessons from Alpha 0. People have worked out the details, have done a lot of work on this type of non-differentiable Newton's method, and it turns out that it has similarly very fast convergence properties as the one corresponding to the differentiable case that you see here, and that's more familiar. So we gave the interpretation of L Bellman equations and the min Bellman equations, the relationship, and so on, how one is obtained as the envelope of the others. And now we want to go into Newton's method and see how this framework of linearizing at the current iterate and then relinearizing again, how it applies to approximation in value space. And all the details are really there in the figures that we saw previously in previous slides. So here we are. We're going to visualize the simple case. This case here, one-step look ahead with quadratic cost function approximation and no rollout. So that's what we're going to do. And, okay, so we have the min Riccati equation and the L Riccati, the min Riccati operator, the L Riccati operator, and we argued that for a given K tilde here to obtain the L, the linear policy that attains the minimum, which is the minimum is attained actually at this point here. That's what we showed. And to obtain this minimum, we have to consider this line, look at all the points of intersection with these blue lines, and take the minimum of those. So the minimum is obtained right at this point, and it corresponds to a tangent, a linearization, in other words, of the Riccati equation. So the one-step look-ahead policy corresponding to K tilde is obtained by this minimization, going down this line and find the point of tangency. And then solve the linearized problem, which gives you the cost coefficient of the online play policy, the one-step look-ahead policy. So given K tilde, we obtain a one-step look-ahead policy, mu tilde, which is linear, and we obtain as follows. We go over here, pick out the tangent, and then find the point of interception with a 45-degree line, and that gives you the cost function of the one-step look-ahead policy. But this is exactly what Newton's method does. So this is the Newton step. Starting from offline training, K tilde, we obtain a policy, an online play policy, whose cost coefficient is this KL tilde. It's a Newton step. It inherits all the nice properties of the Newton step. It has a very fast convergence rate, particularly when you're near K star. Of course, when you're far away from K star, there are complications that we're going to discuss, but when you're near K star, it is very powerful. So that explains also how online play improves on the results of offline training. It's a substantial improvement, and it involves a Newton step. Are there any questions here?
Professor,
Yes.
I have a question. What would happen in case if we assume the cost to be non-quadratic? Would this graphical representation fall apart because we won't have the Riccati equations anymore?
Yes, you have to work to work with the Bellman equation. And there's a similar interpretation for the Bellman equation. The Bellman equation now involves, the Bellman operator involves non-differentiabilities. However, the Bellman operator, and all of these details are in your textbook, the lessons from Alpha Zero. The Bellman operator involves a concave function, like it is here. And regardless of what the state space is and what the control space is, and whether you're working with a continuous problem or a discrete problem, the Bellman equation is always a functional equation. In other words, it admits always an interpretation treatment by means of Newton's method. The functional equation, in other words, x may be discrete, but j is continuous, okay? And it could be that the Bellman equation is differentiable, in which case this interpretation would apply. If it were non-differentiable, then a more general type of Newton's method would apply that is useful for non-differentiable Bellman equation. So that's what would happen in a nutshell. Now, I'm focusing here on intuition, trying to give you the intuition in terms of a simple and relatively familiar special case, a linear quadratic problem. But everything generalizes in a remarkably general way. And this has also been verified, of course, by computational experimentation. Does this answer your question?
Yes, thank you.
Any other questions? Okay, so now let's go back to this unstable policy. So in terms of, and also connect them with the picture for one-step look ahead. Okay, so if we start at K star, okay, approximation value space and start with K star, obviously we're going to get the optimal policy. This is the optimal policy here. If we start with a K tilde, an approximation that's close to K star, to the right or to the left, then we're going to get a one-step look-ahead policy that's close to optimal, but in any case, it is stable in the sense that the optimal policy is stable, has a slope less than 45 degrees, so other policies also have slopes that are less than 45 degrees, as long as the cost function is near the optimal. On the other hand, if you start with K with a K tilde that's further out to the right, then you get a linearization that involves an unstable point. And that is not legitimate, okay? It has a cost function that's infinite. You don't get a point of interception, you don't get, it's not a Newton's method anymore that aims at K star. It may aim at something else, but not at K star. So there's a certain region of stability that's very important in control theory. The region of stability relates to the K tildes, the terminal cost approximations that lead to a stable one-step look-ahead policy. And they are in this green region here, demarcated at one end by the point where the slope of the red curve is 1, okay? The 40 parallel to the 45-degree line. If you start to the left, then you get a stable policy. You start to the right, you get an unstable policy through approximation value space, and that's very bad in control theory, very bad in general, okay? It's a failure for the approximation scheme. Now, this kind of questions are very important in control theory. They are hardly looked at in the AI version of reinforcement learning, but in model predictive control and control theory, these questions are very, very important. How far you can go from optimality in terms of approximation and still maintain a stable policy. Now, if you look at this figure here, this region of stability also happens to be the region of attraction of Newton's method, the set of starting points for Newton's method that yield convergence to the optimal solution. If Newton's method is started somewhere here, then it will work actually, but it will go to this solution, not to that solution. If it started in other examples, if it started outside this region of attraction, it may never converge to anything. If you look at your calculus books at Newton's method, you will see, I'm sure, examples where Newton's method does not converge. It converges within some favorable region of attraction around the solution that you're interested in. And in the context of control theory and reinforcement learning, it relates to the region of stability. So the start of the Newton step must be within the region of stability. But then how do we know what is the region of stability? Okay, well, we don't really know it, except to observe that and in fact it holds in general, that if you start with K tilde to the right of K star, then you tend to be in the region of stability. But what happens if you don't know K star? So how would you know how to pick K tilde to the right of that? And what if you pick it to the left? Well, if you don't pick it too far to the left, then you're going to be safe within the region of stability. But it's possible that you pick it over here somewhere, and then what comes to rescue, what comes to help, is multi-step look ahead and rollout. We will see that multi-step and rollout tends to push you into the region of stability. And that's one of the main advantages of multi-step look ahead. So before now we go to multi-step look ahead, let's look at a visual interpretation of rollout. remember, the rollout algorithm is simply approximation in value space with J tilde being the cost function of some base policy. You remember you did as homework, the traveling salesman problem. There was a base policy, a base heuristic, and the rollout is simply approximation in value space with a cost function, with cost function approximation being equal to the cost function of that base policy. So how do we interpret it in terms of our figures? And we are going to consider a stable base policy whose line has slope less than 45 degrees. Okay. So this is the red curve, the graph of the Riccati operator. And this is the blue line, the graph of the linear base policy. And the cost function of the base policy is quadratic and given by this point here, right? The intersection of these two. The optimal, of course, is here. Now, suppose you do approximation in value space with this, with using K tilde to be the cost coefficient of the base policy. Then the approximation in value space is going to consist of a Newton step. And this is going to be the cost function of the one-step lookahead policy, what we have called the rollout policy. So this is rollout for you. A base policy, which is stable, the corresponding cost, and then you get the cost of the new policy, the rollout policy, and it is a Newton step. If you were to do an additional rollout step, that would be similar. You go over here and so on. This is what policy iteration does. But rollout does what you see here. Are there any questions about this figure?
Professor, I have a question from a student here.
Okay.
1 second. Sorry, which one? Who had a question? Oh.
Hello. Yeah, so I wanted to ask with regards to this slide and also the previous slide. So when we talk about the safe region to initiate the solution, so if we move further to the right, do we risk the Newton steps becoming like too small because of this idea of a vanishing gradient or that kind of an issue because of the asymptotic
Yes.
nature of the curve?
Yes, so if we push it beyond the region of stability, or even if it's close to the edge of the region of stability, if it's close, it's within the region of stability but close to the edge, then its convergence rate deteriorates. Okay, because here the crossing point is going to be very far out to the right. Okay. On the other hand, if you are beyond the green region to the left, then the method will not converge. Okay, it will give you, take you in the opposite direction. In this particular case, it's going to take you towards this solution, which is negative and makes no sense within the linear quadratic control point.
Yeah.
So, yeah, go ahead.
Yeah, so I was saying, yeah, I understand that. And also, like, what happens if we go further to the right of right hand side in this graph, like much to the right? Is there a issue where the steps become too small because of a vanishing gradient kind of a situation?
No, the steps actually become pretty big. Okay, look at this here. Okay, suppose that we take a base policy that is very suboptimal. Okay, but it happens to have a slope that is very close to zero. So you start over here somewhere, essentially, right? You have a slope that's very close to, I'm sorry. Okay. Suppose that you start somewhere over here, okay? Then you linearize and you still are pretty close to the optimal solution. Generally speaking, starting far to the right is far more benign than starting far to the left, okay?
Right. Yeah. So my thought process was, if we are afraid of starting to the left of K star and we want to avoid that at all cost, can't we just choose a very high value of K to ensure that we are much to the right of K star, almost at all possible cases?
Yeah. Generally, that's a good idea, but you should not overdo it. Okay, you should not start too far to the uh, to the um, to the right, because your approximation, the Newton step, is not going to get you as close. Um, the concern here, as far as rollout is concerned, as far as approximation value space, generally it's a good idea to start with K large. Okay, when it comes to rollout, you need to pick a stable base policy, and that's the key concern. As long as it's stable, uh, then at least you're going to get closer to the optimal solution, and substantially closer, because the Newton step is pretty effective on this side. So it depends. Depends how you want to start. If you start with K tilde, then it's one set of considerations. If you start with some base policy, it's another set of considerations. When it comes to choosing a base policy to start rollout with, then the main concern is that it is stable. Now, in the trial and salesman problem, and in problems with discrete state space, usually the policy, this stability concern is satisfied. On the other hand, if you start with J tilde, not J tilde that's necessarily the cost function of a certain policy, then the problem that you're running into is being on the left. But then again, it's not so much a big concern, but it is a concern in model predictive control and control problems in general. And it manifests itself here with linear quadratic problems. In our course, it's not going to be so much of a concern. On the other hand, generally speaking, the concern of being in the region of stability will be addressed by multi-step look ahead in the next few slides.
Okay, thank you.
Okay. So let's go into multi-step look ahead and truncated rollout. Now, the picture we want to look at is this one. This is a more complicated picture, where we have, at the current state, minimization over multiple stages, in this particular case, 2 stages. And then after that, we do truncated rollout with a base policy for a number of steps. And at the end, we have a quadratic cost function approximation. So if this part here would not exist, then you would have approximation in value space with 1 step look ahead, the picture we gave earlier. Now it's more complicated because of the extra look ahead minimization and also truncated rollout. But if you look at this picture, what you see at this layer, at this stage here, after 1 step look ahead, all of this thing here can be viewed, can be lumped together into an effective terminal cost approximation. In other words, multi-step look ahead, even with rollout, is just 1 step look ahead, but with a more complicated starting point that is given by K tilde, acted upon by truncated rollout, and acted upon by a number of look ahead minimization, a number of steps of look ahead minimization. But it is still a Newton step. And what is significant here is to explore what happens, what effect the truncated rollout and the extra look ahead have on this. In other words, how the effective terminal cost approximation differs from the K tilde terminal approximation. And that's what I'm going to try to do in the next couple of figures. But first, we want to visualize value iteration. in terms of our figure and Riccati operator. Now, the value iteration algorithm is simply jk plus 1 equals to what the Bellman equation gives you on the right-hand side, with the j equal to kkx squared. So it is equivalent to operating on the Riccati equation. From kk, the kth iterate, you apply the Riccati operator, you get kk plus 1, and so on. So in terms of our figure, here's the Riccati operator, the red curve, the solution, k star, and given the kth iterate of value iteration, kk plus 1 is f of kk, this level here. We reflect that across the 45-degree line, which is kk plus 1. Now, kk plus 2 at the next iteration is going to be this. You reflect it upon the 45-degree line, you get kk plus 2 here, kk plus 3, and so on. So value iteration is simply this staircase construction on our figure. This is the case where you start to the left of k star. If you were to start to the right of k star, then it would go like this, still a staircase construction. If you were to start, even if you start with some negative values, it will still work, okay? It would converge to k star. If you start very far to the left, beyond this k bar point, then it will not converge to k star, it will converge to it. But it's kind of silly in the context of our problem, because we always want to start with a cost function approximation, an initial k0 that's positive or 0. But the important point I want to note here is that successive value iterations get you closer to k star. And successive value iterations is what we do in multi-step look ahead. And that's why, that's the advantage that multi-step look ahead offers for us, as we would argue. So this is value iteration. And now let's look at the approximation in value space, two-step look ahead, but no rollout. Okay, so let's say that offline training uses us a k tilde that is right here. One step look ahead would go over here and then do a Newton step and come down here. Two-step look ahead would first do a value iteration, go to this point, and then take the Newton step. If you had three-step look ahead, you would go to this point, and then from a closer point to k star, you would get you would try a Newton step. So with two-step look ahead and no rollout, start here, do one value iteration, a Newton step, and that's what you get as the online policy, the one-step look ahead policy. So multi-step look ahead moves the starting point of the Newton step close to k star, and the longer the look ahead, the better. This general rule here that holds for multi-step multi-dimensional problems and so on. Of course, extra look ahead costs time, costs computational resources. Now, this involves no rollout. Let's look at the case where there is also, in addition to multi-step look ahead minimization, there is rollout with a base policy. Okay, this is for two-step look ahead and three truncated rollout steps starting from k tilde. Okay, we start from k tilde. We do look ahead minimization for two steps, 1, 2, and then we do truncated rollout with a stable policy. Now, the line corresponding to stable policy is some linear line, some line that has slope less than 45 degrees. And from this point, we do the 3 rollout steps, and we get to this point. If we were to do an infinite number of truncated rollout steps, we would approach the cost of the base policy. But since we do only 3, we end up short of that. And that's the starting point for the Newton step. But again, multi-step look ahead and also truncated rollout with a stable policy pushes us closer to the regional stability from which we're guaranteed that the Newton step is effective. I understand that this figure is kind of complicated. It packs a lot of insight. There are all sorts of questions that you would encounter in practice. How long should the look ahead be? What's the trade-off between using look ahead minimization and using longer truncated rollout? All of this can be understood and motivated from this figure here. I think it's a complicated figure, but it packs a lot of intuition. And as I will argue later, this figure applies not only to linear quadratic problems in one dimension, but it applies to linear quadratic problems in multiple dimensions, and also applies to far more general dynamic programming problems over an infinite horizon. With discrete state space, continuous state space, everything. It's a very universal intuition in this within this context. Okay, so we said that we interpreted visually rollout. Now, rollout is a single policy iteration. Policy iteration, what's called self-learning in artificial intelligence view, the artificial intelligence terminology of reinforcement learning. Policy iteration is what it's called self-learning, both with the exact implementation, approximate implementation. So policy iteration is repeated rollout, starts with a linear policy, generates a rollout policy, and then uses that as base policy to generate a new rollout policy. And the way this is done is by a 2-step process. In the context of linear quadratic problems, the policy evaluation takes this form. The kth policy has a quadratic cost function, it's linear and stable and has a quadratic cost function. And kk is given by this formula, where lk is the coefficient of mu k, the linear cost coefficient of mu k. So given this policy, we do a policy evaluation and compute kk, and then we do a policy improvement where we obtain the new policy as a linear policy with a coefficient that can be calculated to be in this form. In more complicated problems, of course, policy evaluation may involve simulation, may involve neural networks if it's done approximately, and so on. Policy improvement can be implemented also in a number of different ways, including the possibility of using a policy network. It is very important to use policy networks in repeated rollout. Rollout does not require a policy network or any kind of approximation beyond simulation. But once you go into multi-step, you go into repeated rollout, then the use of some kind of approximation, neural network or otherwise, to do the policy improvement is essential. Now, rollout is a single Newton iteration, and policy iteration is a full-fledged Newton method, a multi-step Newton method. Asymptotically, it solves the Riccati equation exactly, provided you started within its region of convergence. Now, there's also an important many variants of policy iteration, including what's called optimistic policy iteration, which consists of repeated truncated rollout iterations. In other words, policy iteration does not involve truncated rollout. If you introduce, in addition, truncated rollout in it, then you get this optimistic policy iteration, which is used very widely in reinforcement learning. In reinforcement learning, this policy evaluation is done with very few, well, rather, it's not more than infinite number of, it's done iteratively, but with a limited number of value iterations. And this corresponds to truncated rollout. So on this slide, within the slide framework, there are zillions of variations. And once you grasp the basic guidelines and the basic framework of the methodology, then you can implement all kinds of variations and implementations and so on. This is, of course, all of this, of course, is offline training. And at the very end, you get a cost function of a final policy that you can use for approximation in value space. Each iteration now of policy iteration can be viewed, each iteration of each optimistic policy iteration can be viewed as a Newton step augmented by first order iterations, what's called in numerical analysis a Newton SOR step. And usually SOR stands for successive over relaxation. So all of this has a lot of variations, a lot of details that we're going to get into some of this as we go along, but certainly there's a huge methodological framework that includes, is based on this policy iteration. And your textbooks have a lot of details, as well as other textbooks have a lot of details on policy iteration. This is just an overview to construct the broad picture within which policy iteration lives. Are there any questions? Okay, so this is our last slide before we take a break. I just want to alert you that all of this is very, very general. The Newton step interpretation is fundamental in approximation in value space and generalizes very broadly. And your textbook is devoted to a large extent to that interpretation. In particular, it shows how you do this. This involves using Bellman operations in place of Riccati operators. Instead of using Newton's method to solve the min Riccati equation, Newton's method is used to solve the min Bellman equation. Again, approximation in value space is a single Newton iteration enhanced by multi-step lookahead, if any, and by truncated rollout, if any, again. Rollout is a single Newton iteration starting from the cost function of the stable base policy, while exact policy iteration is a full-fledged Newton's method. And finally, as a general rule, multi-step lookahead and truncated rollout enhance the stability properties of the policy produced by approximation value space. It also enhances the convergence rate. How close you get to the optimal policy depends on how much multi-step lookahead you do, how much truncated rollout you do. At the same time, bear in mind that multi-step lookahead costs computation time, and truncated rollout also costs computation time. The computation time for multi-step lookahead minimization is far more than for truncated rollout, because here we minimize over all possible alternatives. Here we just run a single alternative, the base policy, we run it forward. So truncated rollout is much cheaper to implement, and yet it achieves much the same effect as multi-step lookahead in terms of enhancing the stability properties of policy or the convergence rate of Newton's method. So all of this is the broad picture. Within this broad picture, you can design schemes that are governed by your objective, how much computational budget you have, what kind of implementations are useful within your context, whether simulation can be done within your context relatively inexpensively with parallel computation or without parallel computation. There's a lot of play within this picture, but what I want to impress on you is that it is a very general picture, which applies universally in approximation value space. Are there any questions here before we take a break? Okay, so we'll be back in exactly 15 minutes, and you may collect your questions to ask when we return. Okay, so let's start the second half of the lecture. Are there any questions about the first part and the visual interpretations using linear quadratic problems? Okay, so now let's go into problem formulations by dynamic programming and various examples of interest. So in practice, how do you formulate dynamic programming problems? You're typically not given a mathematical representation of the practical problem. You're not given the system equation, you're not given the cost function, you're not even given what the state and the controls are and what the horizon is and so on. So it is an art on how you pass from a practical problem into a mathematical problem that you can solve using algorithms. And this can be approached in many different ways in the context of dynamic programming. I cannot give you the range of approaches. I can give you an idea of what I do, okay? My way of approaching this issue is to look at the practical situation and define first the decisions. You can easily pretty well figure out what it is that you have to decide. Like for example, you're traveling salesman context, what you need to decide is from one city to go to the next city. These are the decisions that you make. Then you need to decide what the stages are. Particularly for a stochastic problem, the stages are demarcated by when information arrives to you. When new information arrives, that's the time to adapt your policy and to choose the control based on that information. And the last thing that you would look at is what is the state. And here, there's some ambiguity because there are many different quantities that you can consider legitimately as states in a given practical situation. But generally speaking, it is a good idea to try to define a state, something that summarizes the past for purposes of future optimization. In other words, what is significant to know right now for the purposes of making good decisions in the future? Or otherwise put, the kind of quantity that you want to consider state is those that when you know it, all past information is irrelevant. That's the necessary information for the future decisions. And the rationale for this is that control applies action that depends on the state. So the state must subsume all the information that's useful for decision control. That's fairly evident. Let's look at some examples. In the traveling salesman problem, you need to include all the relevant information in the state before making a decision of which city to go to. And what might be the minimum of that relevant information? Well, you need to include the past cities that you have visited, as well as the current city where you are. Other information, such as what costs were incurred in the previous stages, or the order of that you visited the past cities is not necessary and need not be included in the state. Of course, you may say, I'm going to include it anyway. That's fine, but your state is going to grow bigger, essentially, and there may be some inefficiency associated with that. Now, here's an important class of problems where what is state is a significant issue. These are the partial information problems or imperfect information problems, where there is some quantity of interest that you would like to introduce a state, such as, for example, the position and velocity vector of a moving object. However, the problem is that you don't know that. You don't have perfect information of the quantity that ideally you would like to include, to call state. Instead, what you have is noisy measurements, which of yk, and that's all you have on which to base the control. For example, in the case of a car moving on a straight line, ideally you would like to know the position and the velocity vector of that that car. On the other hand, you may be measuring the position and velocity by radar, which may be imperfect. They have noise. So you don't really know what the vector is, but may have a probability distribution of what this vector is. Now, what would be state in this context? It's all the information that summarizes the past for the purpose of future optimization. So it is correct to use IK, namely the collection of all the measurements up to time K. It's a legitimate state, and it may be useful in some contexts too. On the other hand, there are alternative states. And a very, very important one is the conditional probability distribution of the quantity of interest given the information that you have collected so far, given all the measurements. This is called the belief state, or you can view it as a probabilistic state. And it turns out that it also subsumes all the information that's useful for the purposes of controlled choice. So that's a common formulation of this imperfect state information problems, reformulating the problem as a perfect state information problem that involves a state, this belief state, this probability distribution. Of course, that presupposes also if you must have some kind of algorithm that estimates this probability distribution given the measurements and updates this probability distribution as you go along. So these are some examples of reformulation of state control and of states and controls and so on. And let's go to a general device that can be used for problem reformulation. And that's the device of state augmentation. In state augmentation, you have something that appears like would be desirable quantity to view as state. On the other hand, it may not quite be sufficient to give you the framework that you want in terms of a system equation and so on. So you augment it, you make it bigger, you add more things to the state so that it becomes legitimate in some sense in the context of our dynamic programming framework. And a simple example of this type of situation is when there are delays on the effect that controls and previous states have on the next state. So in other words, instead of the next quote unquote state, instead of it depending on the current state, the control and some random disturbance, they may be dependent on the state before and also on the control before that. And this effect manifests itself with a delay of 1 unit in this particular case. There may be delay of multiple units in other cases. This is a common situation in many contexts, particularly in chemical process control, where you do something now, but its effect on the state does not manifest itself until later, like a minute later or an hour later. You change a variable now, and it takes some time for the flow of material to get to the point of interest where it has an effect. Very common problems with delays. On the other hand, conceptually, delays can be treated by reformulation. In particular, in this one-step delay situation, we introduce additional state variables, which we call YK. YK is the delayed state. SK is the delayed control. And we write an augmented system equation where xk plus 1 is given by this formula with the additional state variables introduced. This stands for that, and this stands for that. And the additional state variables propagate according to this equation. So now we call the triplet of x, y, and s the new state, and it enters in the right-hand side as x, yk, and sk. And this equation is of the form that we know and can use for dynamic programming. It does not involve any delays. So we call this x tilde. So this is x tilde k plus 1. xk, yk, and sk is called x tilde k. uk appears here. wk appears here. And f tilde k is a multidimensional version of this equation here. It's a new equation, a new system equation with a bigger state vector. And now we can work with that in the dynamic programming framework that we know. And the Reformulate dynamic programming algorithm in terms of this new system takes this form here. On the right-hand side, you have the one-stage cost, and you have the cost to go from the next state that you end up with, but the next augmented state. It involves this part, and this part. It is still a legitimate dynamic programming equation. You take the expected value of that, minimize with respect to UK, and then what you get on the left-hand side is something that depends on the new state. In other words, on xk minus 1, and uk minus 1, which also appear here. So at time k, you measure your current state. You have kept in memory the delayed state. You have kept in memory the delayed control, the control one step earlier. And then you do this minimization. And of course, you need to carry in the exact dynamic programming algorithm, or in an approximate version, a bigger function that involves dependence on 3 state variables. So you carry this backwards, starting from this terminal state, terminal condition, and you go backwards and you reach the initial state. And that's the dynamic programming algorithm that you can use exactly, or more likely with approximation. There are many types of state augmentation that are along this pattern. Your class notes involve, give you a number of other examples. One possibility is when you have a forecast of future uncertainty. Like at the present time, when you apply the present control, you get a forecast that the weather 2 days from now is going to be so-and-so, okay? And that may affect your decision. Then the forecast has to be included as part of the augmented state. There are other examples like that, and I'll let you read the notes and the literature. Are there any questions here? Okay. There are many problems that have a terminal state, a natural terminal state, which is cost-free and absorbing, in the sense that once we get there, we can't move and we don't move and we incur no cost. On the other hand, reaching, we don't know when we're going to reach the terminal state. Like, for example, in the game of chess, there's a terminal state when the game ends, but we don't know how long the game is going to take. Generally speaking, we can view these problems with terminal state as infinite horizon problems, where once you get to the terminal state, the dynamics of the problem is that you stay there at no cost. Okay? This is always a possibility. But there's also another possibility to convert the problem into a finite horizon problem by introducing as horizon an upper bound to the optimal number of stages, assuming that you know such a bound, and then add a big penalty for not terminating before the end of the horizon. In other words, you try to discourage trajectories that run you beyond the end of the horizon. That will also work for some cases. And let me give an example of this. It's a problem involving multiple vehicles that move within some network of routes. And the objective is to reach some tasks and to perform these tasks. And that's when you reach the terminal state, when all the tasks have been performed. Okay. Think of delivery vehicles having to deliver products to various places. There are many problems of this type. So in this particular case, there are two vehicles and there are two tasks. One possible cost function might be to minimize the number of moves to perform all the tasks and reach the terminal state. So these vehicles move simultaneously, one step for each stage. And how would you formulate this as a finite horizon problem? Well, you know that one possible solution is to take a route from here to here. That's the longest path from vehicle 2 to this task, and the path from this vehicle to this task is 1, 2, 3, 4, 5, 6 steps. Okay, so you can have a horizon that's 6, and also have a big penalty for not terminating before for not terminating after 6 steps. Of course, it's possible to get to both of those in 3 steps. And in fact, the optimal solution is what you see here. But that would be a formulation as a finite horizon problem. Now let's focus on this multi-vehicle routing problem, because we're going to look at problems of this type quite a bit later in the course. How would you formulate this problem as a dynamic programming problem? Any suggestions? What would be the states? What would be the controls? What would be the terminal state, the horizon, and so on? Any suggestions?
Hello, Professor. Can you hear me?
Yes, I can hear you.
I guess that the state can just be like the position pair of both vehicles.
Yes.
And
Is that enough? Is that enough?
and whether it is whether that vehicle has finished its task or not, maybe.
Well, the vehicles are not assigned to tasks. In other words, it's possible for this vehicle to go to this task, and for this vehicle to go to this other task. Or it may be that they both start going towards the same task and then reroute themselves. Okay. So what would be useful? The question to ask here, what would be useful for the purposes of future optimization? Given that you are in the middle of the game, the vehicles have moved around and they have performed some of the tasks. Certainly the position of the vehicle, the pair of the two positions should be part of the state, but also the location of the tasks that are unfinished would also be interesting, right? And would guide future moves. So the state, one possible state, perhaps the best in this particular context, would be to take the pair of positions, current positions of the vehicles, and the lists of tasks that have not been performed. And the controls, now what are the controls, by the way? Controls would be the joint moves, okay? So this is one control, that is one control, this and that is another control, and so on. So it's the pair of joint moves, that would be the control space here. Terminal state, well, the terminal state should be when everything is finished, right? It's absorbing because there is no more cost left and the problem terminates, the problem finishes. And the horizon, you can take it an infinite horizon or a finite horizon with as many as 6 steps or something. Now, what's the problem size here? Well, look at the pairs of possible, well, look at the states. Instead of all pairs of positions, also number of unfinished tasks, this can be astronomical, right? I mean, if I have, even for problems with even for this problem here that has only 12 nodes, okay, these numbers are the node numbers. Still, the number of states is quite substantial. The number of controls is also substantial. Each vehicle has a number of choices at each step, and there are 2 of them. So it's the number of choices to the second power. If you had 20 vehicles, it would be the number of possible choices to the 20th power. Already it becomes very big. So the control space would also be very large, even for a modest number of tasks and vehicles. So this type of situation where you have multiple components of the control vector resulting in an exponential growth of the control space with the number of vehicles is a good candidate for a multi-agent framework that we are going to talk about quite a bit in this course, and we're going to introduce in the next couple of slides. So what do we mean by a multi-agent problem? It is a situation where we have multiple decision-making entities, which we call agents. In this case, there are 5 agents, and each agent has a control vector of his own. And the overall control vector for the problem is the Cartesian product, okay? That has as components the agent decision component. So if each of these UIs takes even a small number of values, if you have a large number of agents, the number of these M tuples becomes quite big. Now, these agents make decisions in stages, and they collect information about the environment, and either on their own or through information exchange from some computing cloud, and they transmit to each other. They share selectively with each other. And based on this information, they apply a decision. Then we go to the next stage, we collect new information, share new information, make another decision, and so on. Needless to say that this is already a pretty large size problem, particularly due to the size of the control space, but also due to the size of the state space potentially. And there's a major mathematical distinction between these problem structures. One is they both have to do with how information is shared. And there is the classical information pattern where the agents are fully cooperative and fully sharing and never forgetting information. So this is as if they all have the same information, and so they can be viewed as one. And you can write a dynamic programming algorithm for this situation. The more challenging situation is when the agents are partially sharing the information, so they may have different data to go with. And even worse, if they are antagonistic, particularly if they have different objectives. This is really a very hard problem. But even if they have the same objective, they could be sharing the only partially the information. And that is a hard problem, much harder than this one, primarily because it is hard to treat by dynamic programming. Actually, this type of problem is very old. I looked at this problem for about 6 months when I was a PhD student, long time ago. And I decided that was, okay, this case was not very interesting. It was just dynamic programming. The computational issue did not enter into the picture at that time because people did not have powerful computers to use the kind of methodology that's being used today in reinforcement learning. So from the theoretical point of view, this was dynamic programming, not very interesting. This was the most interesting part, but I looked at it for 6 months and decided it was just too hard for me. And I'll never get my PhD in this area and with interesting work that people would pay attention to. So I gave up and turned into a different direction. And I did the right thing because research in this field went on for quite some time, like 10, 15 years subsequently, and gradually it sort of petered away. And people reached a point where they could not produce any meaningful results. But this problem area was revitalized when reinforcement learning came along with its powerful computational arsenal and problems that were thought to be impossible to address. In the past, with reinforcement learning, they became, in approximations, they became more feasible. So we're going to look at these problems from the point of view of reinforcement learning, but we are going to focus on classical information patterns to begin with. We will generalize later, but we'll start with classical information pattern, whereby the agents have exact state information and they choose their controls as a function of the state, and they know the same state. So this is as if there's some cloud here that is a clearinghouse of information. It collects all the information of the agents, perhaps collects some further information of its own, and it passes some kind of state information as needed to the agent. So this becomes classical dynamic programming involving a system with some state X and some control U, possibly stochastic system. And the characteristic feature of this problem and the most challenging part of the formulation is the fact that the control has M components corresponding to the M agents. And that explodes the control space, making computations very challenging. Let me also mention here that agent is just a metaphor here. The important structure from a mathematical point of view is that U consists of M components. These components may correspond to agents traveling in a geographical area, like the trucks that in a multi-vehicle routing problem that go around in different locations, and they get their information perhaps from a central dispatcher or by communicating through some kind of channel with each other. But the agents don't have to be geographically separated. They can inhabit the same robot, for example. These U's may correspond to the actions of different arms of the same robot. So the important thing is the mathematical structure of multiple components and the computational challenges that it poses. And what we're going to do is reformulate this problem for faster computation to address this challenge here of the exponential size of the search and control space. And later, we're going to discuss the case where we don't have a classical information pattern, but still we compute these controls in a distributed fashion, and perhaps we try to guess what other agents are doing, and things like that. This will come much later, but let me give you an idea of how we deal with the large control space size by using reformulation. Okay, so this is a fun example. It involves spiders and flies. And the spiders are trying to catch the flies. In this particular picture, there are 15 spiders, and they move in the 4 directions, or they can stay where they are. So each spider has 5 degrees of freedom, 5 choices at each time step. The objective is for the spiders to catch the flies in minimum time. And the flies are passive and blind. They may stay still or they may move randomly. However, the spiders can observe the flies. They know where they are at every step. So the challenge here is how to select at each stage a joint move for all the spiders. And there are 5 to the 15 possible joint moves, because there are 5 spiders, there are 15 spiders, each one has 5 possibilities. So the number of possibilities is 5 to the 15. And with our methodology, we're going to reduce the 5 to the 15 to the 5 times 15, which is much more manageable, while at the same time maintaining good algorithmic properties. For example, we're going to discuss rollout algorithms that work just as well with that many choices as with that many choices. And the idea for that is reformulation and change the control space. Change the problem where the control is not a joint, it does not consist of the joint moves of spiders, but rather consists of a sequence of one spider at a time move. So there are 15 moves of that type, each one with 5 possibilities, and the total is 75. And okay, there are some videos. There's a lecture on this material, multi-agent problems, and you can find this some illustrating videos and explanation of what I've been saying here, elaboration in this at this link. We're going to do that later in the class. But let me give you an idea of how the reformulation goes, how we get from here to here. It's an old idea which reformulates the problem, trading off control complexity for state complexity. Introduce more states for less controls at each step. And the way we do that is by unfolding the control action to pass from a state to the next state. We apply the M controls sequentially, one at a time. So from this state, we apply control U1, get to this state. Here we apply control U2, get to that state. Here we apply U3 and so on. And after M-1 steps, we get to states like that. And then we apply the final control. And it's only at this time that we involve a cost, the cost of the stage from X to X bar. And also we determine the transition. The transitions here are evident. Transition from here to here is given by the last step. So now the control space has been simplified a great deal because it involves only one control component at a time. And however, what's happened now is that the number of stages has increased by a factor of m, and also the cost functions of the problem, the state space has become more complicated, and the cost function of the problem involves a cost function for this type of state, for this type of state, and so on. So there are many more cost functions. So smaller control space, larger state space. On the other hand, some algorithms, they're not bothered by large state space. And what's important is the control space. And one of them is rollout. Rollout for this problem here, the reformulated problem, is much simpler. And this is the kind of algorithm that we're going to study. And rollout, the key thing is that rollout is not affected by the size of the state space. Rollout cares only about the number of successor states to each state. In other words, the number of controls here, the number of controls here, and so on. And only one state and its successors are looked at this stage during the rollout operation online. And the key fact here is that this is a legitimate problem reformulation. This is a legitimate rollout algorithm, and it inherits the Newton step properties of rollout. And it turns out that with this reformulation, you do almost as well as you do with the original problem, where the control space is very large. And you get a complexity reduction. The one-step look-ahead branching factor is reduced from n to the m, the exponential increase. Instead of increasing exponentially, it increases linearly, where n is the number of possible choices for each component UI. So we are going to revisit this formulation and problems of this type in a few lectures. Are there any questions? Okay, so let's look at partial state observation problems, also a very, very challenging class of problems and also very useful in practice. Let's start with an example. Suppose that you have a car that's looking for a parking space. Now, the parking spaces are on this line, okay? There are capital M of them. And in this simple version of the problem, we assume that the parking spaces are arranged in a line. And the car can go in other directions. If it is at this location, it can go either to the left, it can go to the right. And it observes the state of the parking space, whether it's taken or is it free, once it gets there. So at this point, it knows that what the state of this parking space is. And if it is free, it can park there, or it can continue looking for a better space. There's a cost for parking at each one position. C1 is the cost for parking at position 1, C2, and so on. And then once we park, we reach a termination state, but we don't know when this is going to happen. So at each time step, we move one step in one spot in either direction, decide to park or not at spot M if it is free, and if we decide to park, if the cost is C sub M. And if we have not parked, like that, time M is an artificial horizon here. There's a large cost C. Now, we could have perfect state observation here, whereby the map of the parking lot is known to the car, but we don't assume that. We assume that the car does not know whether the spaces are free or taken. Instead, it just travels to a particular place and it looks at it and sees whether it's free or not. But to make the problem more complicated, not only we observe the free taking status of only the spot that we are in, but also the parking spots may change status in the next time step with some probability. Now let's think of a situation where there are other cars also looking for a parking space, and even though you've seen a parking space that may have been expensive at some time, and you've gone on to search from a different for a different parking space, you are not assured that when you come back to that parking space that you observe to be free, you're not sure if it's going to be free. It may have been taken. And we assume that each parking spot may change status at the current time step, at the next time step with some probability. So a natural state here would be the map of the parking lot. But that map changes all the time probabilistically because of the fact that new cars come in and existing parked cars may decide to go out and free the parking spot. However, the status of the spots can be estimated in some probabilistic sense based on the observation. We have observations, we observe some parking spaces, and we have these probabilities by which the status of the spaces change. So we can construct a probability distribution for the entire parking lot of free and taken spots. So what should the state be in this context? Well, it should summarize all the information needed for the purpose of future optimization. This provides a guideline. And one possibility, a first candidate, is a set of all observations so far. That summarizes all the information we ever got, and that's the best we can hope for. However, there's another candidate, the belief state, of which I talked about earlier, namely the conditional probabilities of the free taking status of all the spots. So this is a probability distribution with a probability for every spot. So P1 may be like 1/2 and 1/2, 1/2 being free, 1/2 being empty, being taken. Similarly, piece of M is maybe 1/3 being free, 2/3 being taken, and so on. So this is the belief state of the parking lot, conditioned on all the observations we have so far. And this is something that we can keep track of based on the observations that we have, and it can serve as a state in a dynamic programming algorithm, an algorithm that is typical of these problems with partial state observation. And I'm going to give this algorithm in the next slide. Are there any questions here about this example, or lots of the meaning of partial state observation and belief state? If you guys have understood that, then I'm very happy, because this is one of the most challenging concepts to grasp in dynamic programming. On the other hand, this example is kind of intuitive, and perhaps you find it a good introduction to this partial state observation problems. Okay, a rigorous mathematical formulation of these perfect state information problems, and also how you construct an equivalent dynamic programming algorithm is long and tedious, and we're not going to go through that. Instead, we're going to give a dynamic programming algorithm that has an intuitive character based on what we know so far. So you have to think of here of a reformulation involving a new system. And this is a system by which the belief state, the probability distribution over some original state space, this belief state is denoted by BK. You have to think of a belief state system whereby the belief is updated in response to controls applied and also observations that you obtain from the environment. All of these, of course, are probabilistically tied, and the observation is a stochastic variable that depends on the state and the control, and by extension on the belief state. So we have a probability distribution for this observation based on what we know, which is the belief state pk, and based on the control that we apply. Now, this belief state evolves over time. The belief state is perfectly known to the controller. The original state is not known, but the belief state is given by this estimator or belief state system. It's known by the controller, which applies a policy, a function of this belief state, and this is the control that we use at time k. So now, what would be the form of a dynamic programming algorithm? The state here is this belief state. So on the left-hand side, we have the optimal cost to go at stage k as a function of the belief state dk. On the right-hand side, we should have the immediate cost of the current stage plus the cost to go from the state where we're going to land. Now, the state where we're going to land is given by this belief estimator. It's a function of bk, uk, and the new observation. Now, this is a stochastic quantity, and we take the expected value of this. It's stochastic because of zk plus 1. Zk plus 1 plays the role of disturbance here. And we take the expected value with respect to zk plus 1, and the probability distribution of zk plus 1 can be computed the conditional distribution of zk plus 1 can be computed. It's conditional with respect to bk, given bk, and given uk. In practical problems, the conditional probability distribution of zk plus 1 is given as a function of the original state of the system and uk. But you can calculate this conditional probability by using this belief state. It's a matter of probabilistic calculation. And there is also UK is a control constraint set at time k, and this one stage cost is the expected cost of stage k. It's the expected cost of the original problem with the distribution of xk and wk determined by the belief state and the distribution of wk. In other words, from this and the belief state, you can calculate this cost as a function of bk and uk, and this is what we use in this algorithm here. So all of this, of course, is predicated in having a belief estimator, and that may be a challenging part of the problem. And the other challenging part is that this algorithm, even if the original state space was finite, this algorithm is executed over an infinite state space. The space of belief states is a set of probability distributions, and that is a continuous space. It's the simplex, the unit simplex, right? That's where probability distributions live in. Therefore, to solve this problem, you need some kind of discretization or some kind of approximation. It's extremely difficult to apply this dynamic programming algorithm in exact form. It's only a handful of very, very trivial problems where you can solve this dynamic programming algorithm exactly. You have to use approximations, and a challenge here is the infinite character of the belief space. The character of the control space remains unchanged. So if U lives originally in a finite set, it will still live in a finite set here. And that's very useful from the context, from the point of view of rollout. If you apply a rollout within this context, then there's only a finite number of controls that you need to choose from at every stage. The size of the state space does not matter. It's the size of the control space that matters in the rollout context. So we will see examples of application of rollout to partial state information problems. And overall, despite the challenge of these problems, rollout has done very well for given the circumstance. So we're going to touch upon this problem as we go along in various contexts. And that brings us to the end of this lecture. Are there any questions? Okay, the next lecture is going to be, we're going to complete our overview of the material of this class. We've been going quickly through various concepts because this is just an overview. Now we're going to get more deeply into various topics. And in the next lecture, we're going to spend some time to discuss adaptive and model predictive control. We're going to see that this has close relation to the AlphaZero architecture. And we'll discuss the special issues of approximation in value space in that context. And then we're going to go into more in-depth discussion of rollout, the cost improvement property that I mentioned in the past, and various types of rollout algorithms involving various types of approximation. Okay, there will be a homework due in 1 week. Exercise 1.2 of the class notes. This is a rollout type problem. It's quite substantial. You'll have to do a lot more work than you did for the first homework problem. The other thing is that even though we give a solved example of this exercise, the data that you are supposed to use for your solution is different. So you'll definitely have to do your own calculations. So hopefully the solved example can provide you with a guideline for structuring your solution. After we discuss adaptive and model predictive control, we're going to be in chapter 2 territory, which starts with the discussion of rollout. And it would be a good idea to read ahead. And it's also a good time now to watch summary video lectures. There is a 1-hour version of this summary that I gave a couple of months ago, 3 months ago at MIT, based on the book Lessons for AlphaZero, which has all these Newton interpretations, one-step look ahead, multi-step look ahead, and so on. There's also a multi-agent video lecture that I gave here at ASU maybe a year and a half ago or so, which you can look at it here and try to correlate these video lectures with the material of the course, my lectures, and also the lecture notes in your homework also. So that's all I have for today. Any questions? Okay, guys. Nice to see you, that you're real live persons in this room with Jameson. And like I said, I'll be glad to meet you in person. And if you see me in the corridor, or if you happen to be at the 5th floor of the Brickyard where I have my office, and you see the door open, just pop your head in and say hello. We'll see you next week.